Okay. So in the previous class, no, we were discussing about what is an algorithm, and then we saw when an algorithm is given, how to analyze its time complexity. So in this class, let me give some more example on space complexity. In the previous examples, we discussed only on time complexity. So first, I'll quickly give some examples of how to see the space complexity. After seeing the space complexity, we will be discussing on asymptotic notation, which help us to analyze an algorithm's time complexity, right? So let me show my PPT to you. Okay, I hope you can able to see this. So we already know why we want to analyze an algorithm. Why we want to analyze an algorithm? Because algorithm is a step-by-step procedure to solve any particular task or any problem. So when we want to solve any problem, we may be having many different solutions for it. So we want to choose the best solution among that. So to do that, we want to find which is the best algorithm, right? So we have to analyze it. So we can analyze an algorithm by its time taken and also by the space occupied by it in the memory. So I hope you all got some idea on how to calculate the time complexity. Now let's discuss on space complexity as well. So if you see this example, here it is on swapping a number. So if you consider this is an algorithm for it, so it's begin and we want to swap, right? So first I have taken a temporary variable. There we have kept the first variable a in it. Then in this a we are assigning b, and after once b is assigned to a, now in the b we can assign temp. That's what algorithm you all know, to swap two numbers. So let's see what will be the space complexity. Okay, if I want to say the time complexity, you all know this statement can be taken once time one operation to do this, and this statement will take another operation to do this, and this operation will be taking another operation to do it. And so three statements are there. So how will I find the time complexity? We'll be adding 1 plus 2 plus 1 plus 1 plus 1, right? So that is how we'll be doing here. So space complexity is like time complexity is like 1 plus 1 plus 1, which is equal to 3, and it is a constant. So we know whenever it is a constant, any number, maybe it is 3 or it is 1000 or it is 10,000 or it is 3,000, whatever may be the value, whenever you get a constant value, we will be denoting that time complexity as big O of 1. So that is what the time complexity, which you know already. Now we want to talk about space complexity. So if I want to say about the space complexity, you can see here. So we want to see how many number of variables are used. So because space complexity means what, we have to say how many memory spaces occupied by this algorithm. So which are usually variables are used to store some data in it, and that will be occupying some memory space. So we have to say how many number of variables are used in this algorithm. So we can say temp is one algorithm, a is one algorithm, b is one algorithm. So totally three variables are used. So you can see a, b, and the temp. So totally we are using three variables. So here we are using three variables, and I already told you whenever we get any constant, we'll be representing that complexity as big O of 1. Even 3 or 3000 or 300 or 10 or 20, whatever it may be, the time complexity of the space is also big O of 1. And here you can just see these are the common notation generally we'll be getting when we analyze the time complexity and space complexity, right? This is what. And here you can see it is arranged in an ascending order from big O of 1 to big O of n factorial, right? So the, like whenever we want to, so we know, we already in the class we have seen so many time complexity. We saw big O of n square, we saw big O of root n, we saw log of n, like that we analyze many things, right? And also we saw log n, like that we have many way of representing our time complexity. So when we want to arrange all this time complexity measurement in an ascending order, this is the lowest is like big O of 1. And then we have big O of log n, big O of n, it will be like average, and then we have big O of n log n, n square, n cube, 2 to the power of n, and n factorial. So this is the toppest one. So here you can see, other than this, if you have anything, it will be the multiples of this only. So generally, this is how we will be representing our time complexity. The lowest is from big O of 1, and the to the highest of big O of n factorial. So you can just know the orderings. So who comes after whom, like that. I hope you're all following me and you can able to hear me all as well, ma. Okay, so let's go to the next example. So here again, time complexity you know already. For every statement, this statement will be taking a time of 1. And here for loop means since it is going 0 to n less than n, so it will go for n to n plus 1. And this statement will be executed for n times. And so if you find, if you sum up all this, the highest degree of polynomial you will be getting is big O of n. So now our objective is to know what is the space complexity of it. So space complexity means what will you do? You have to see what are the variables used in this program. So s is one variable, so it is represented here. And the next variable is I, so I is represented here. And the next variable is this array, right? This array. So array, what is the size of an array? So array size is going till I. So the I value will be ranging to 0 to less than n, right? So we can say it is n value. So the array will be occupying, the array size will be n. So here we have given the array size will be n space. For example, if the array size is can be 3, which means if the n value is 3, then the array size will be 3. If the n value is 5, and the array will be of creating for 5 memory spaces, right? 3, 4, 5. So here that is why we have given array. What will be the size of this array? The size of the array will be n. And then what is the other variable? Here it is used is n. So n is also given here. So here we will be having n plus 3. And we know that always in this big O notation, we will be taking only the highest degree of polynomial and the constants will be ignored. So we don't want to consider this constant. So what will be the value? We will be considering n. So the space complexity is big O of n. So this is the next example, and the next example is this. So here already we know here we have a for loop, nested for loop, one for loop present inside another for loop, and the time complexity already we have discussed, right? This for loop will be executing for n plus 1 time. So this one is to the last false condition to check, and this things the inner for loop is the body of the outer for loop. So here you can see this is the outer for loop, and this all the body of the inner for loop, right? So inner for loop. Okay. So for this inner for loop will be executed for n times. And then this, let us come to this for loop. So this for loop will also execute for n plus 1 time. Since already this inner for loop is a body of the outer for loop, this for loop would have run for n times, and this statement would have also run for n times. And then when you come to this for loop will be executed for n into n plus 1 times. This n is, since it is a body of this for loop will be executed for n times, and this for loop itself will execute it for n plus 1 times, and this c will be executed for n times, which comes from this outer for loop, and because of inner for loop it will again execute for another n times, so n into n. So when we add all these things, we will be having, it will be like n plus 1 plus n into n plus 1 plus n square. And when you solve it, you will be getting n square plus n square, and you will get 2n square plus 2n plus 1, something like this you will get, right? And here if you see, all the constants will be ignored and you have to take the highest degree of polynomial. So it is n square. So we will be getting big O of n square as a time complexity, let it be. Now, what we have to do now, the next thing is space complexity. So, already I told space complexity, you have to see what are the variables used here. So, what are the variables used here? I is one variable. So, here you can see I, and that is one variable, right? Whatever a memory space will be allotted like this I in the memory, and we'll be updating the value of I. Similarly, we have a memory space for J as well. So we'll be updating the value of j here. And then another space will be allotted for n, which says how many number of times this for loop will be executed. So that will be occupying another space. So then we have three arrays, right? And here we have consider square matrix. So square matrix means it will be like 3 into 3 or 4 into 4, 4 cross 4 or 2 cross 2 or 5 cross 5. So this like only our matrix size will be, right? So for example, C. So C is also an array. So how does what will be the size? So for example, if the since it is a square matrix, so for example, we will be getting n cross n matrix. So if for example 3 cross 3 or 2 cross 3. So each and every, so we'll be like taking an array format of this type, right, to represent this memory. If it is 2 cross 2, so we'll be having like this, 2 rows and 2 columns. If it is 3 cross 3, accordingly you will be taking a memory space like this. So for each and every, so it is a square matrix, it will be taking n square size for each, storing one matrix. And then here how many matrix like that we have used? C is one matrix, A is another matrix, B is another matrix. So each and every matrix will take n square of size, okay, in the memory. So why n square? Because it is a square matrix, so it will be like 3 cross 3 or 2 cross 2 or 4 cross 4, all these things. DA. So we have n cross, like we have n square is the size of this matrix. So when we want to find the space complexity, how does it come? It will be like 3n square plus 3. So from this we'll be ignoring all the constant, and we'll be taking the highest degree of polynomial, so it is n square. So here is another example. I hope now you have understand how we'll be calculating the space complexity. Time complexity already you know. I think I don't want to repeat it. I'll upload this PPT in your GCR. You can just look on it. So space complexity means how will you calculate? Again, we have to say what are the variables we have used here. So I is one variable, n is another variable, j is another variable, and here how many matrices? K is another variable. So like n, I, j, k are the variables. And then how many matrix are used? C is one matrix, and A is another matrix, B is another matrix. Again, it is a square matrix. So like it will be like n cross n matrix. So each and every array, for example, C array will be taking a size of n square. Similarly, A and B, every one will take a size of n square, because n cross n matrix, so we'll get n square can be considered. So for this code, we can say 3n square plus 4 other variables. And ignoring the constant, taking the highest degree of polynomial, you will get the time complexity of big O of n square. And so this is another example. So here you can see this examples I have already discussed in the class. Okay, so I hope you would have understood how to calculate the time complexity and space complexity. Is it not, Ma? Can I get some response? Have you understood how to calculate the space complexity also from this?
Yes, ma'am.
Yes, thank you, Madan. I hope others also have understood. Yeah, thanks, Shavani. Okay, ma'am. So now, so this is not new to you. Anyway, you know already. Thank you, Harish. You know already about all these things. I just want to recollect, because once again in the DA. So in design analysis of algorithm also you should know all this concept. Okay, the next thing is generally whenever we talk about an algorithm and you want to find the time and space complexity, we will be using asymptotic notation. to do this time and space complexity, right? In the asymptotic notation only, one among the asymptotic notation is big O. So until now, we used so many examples, and from there we found the big O notation, that is worst case time complexity, right? And worst case space complexity only. So if I run this algorithm, this is the worst case of it. Above that, the time complexity will not go. So that is what we discussed until now in an example. So in asymptotic notation, we have three notations to do. So let us see in asymptotic notation. What is the purpose of asymptotic notation? Asymptotic notation help us to find the time complexity using three notations. What are the three notations? Can someone tell me, ma? What are the notations we have in asymptotic notation to do the complexity measurement? One is big O, right? So one is big O. So we'll be using this big O notation. This is first asymptotic notation. So this will be talking about worst case time complexity. And the second one is omega, right? Omega. So omega speaks about the best case time complexity. And what is the other one? Can I get a response? What is that one?
Theta.
Theta,
Theta.
very good. Theta, yes. So theta speaks about what?
Average case.
Very good. Average case time complexity. So let's quickly recollect about all this one by one. So first let us say about the big O notation. So in big O notation, can you tell me what is the definition we have already learned in data structure for big O? When will I say big O notation is true? Big O is
F
representing.
of n is less than or equal to g of n.
Excellent one, excellent. You are remembering all these things. I just quickly recollect here. So, for example, let me take our algorithm's time complexities f of n. So, when I say this f of n is true, means always this f of n should be less than or equal to big O of g of n. So this says about the like what worst case time complexity. So this will be true if and only if. How will we represent? So f of, I can say like this, f of 1 is equal to big O of g of n if and only if this f of n should be less than or equal to big O of g of n for all n naught, and the constant c should be some greater than this n value, should be greater than this n naught value. For example, if I want to say like this graph, for example, if my function which we found, our algorithm is f of n, and this f of n should be always less than, or I can say it should be always less than g of n. Okay, so this f of n will be always less than g of n. It will not cross this g of n. Such function only we are finding in the big O. That is worst case complexity measured by this big O of n. Big O. Okay, and then we say that this n. So we know that from some particular point of time, from that only it is always going up. So that's n value, this value is called n naught. Okay, so this big O of g of n is always represented as c into g of n, and this we have to find what is this constant value, and this we have to find what is this n, from which n value it is true. So that value will be measured by n naught, and the difference between these two is said to be as c. So from a particular point, always from that, because some value can be ignorable, because sometimes, for example, for an input of 1, 2, 3, or up to 6, we cannot predict. But this small amount of input can be ignored when you have a billions of input, right? So So we have to find what is this C constant, and from a particular value of C and from a particular value of n naught, this value will be, this condition will be true. So this is how we will be denoting this big O of big O notation. So let us see this with an example. For example, if you consider our algorithm, that is f of n can be like 2n plus 3 or any quadratic equation, right? Generally, in the PPT also we saw whenever we measure any of this, we will be getting some quadratic equation only. So this is what the quadratic equation we got, right? So here also I have mentioned this f of n, some function which I am going to get is 2n plus 3, and so this should be, and we have this is what we have equated. F of n should be always less than c into g of n. So big of g, this is rotated by c into g of n. So it is like c into, for example, we know always this g of n should be greater than this. So we can consider same kind of quadratic equation. Let me say it as n. Okay, for this g of n, I am giving the value of n. So we have to find for which value of c and for from which value of n this condition will be true. What is the condition? Always the f of n should be less than or equal to this g of n, c into g of n. So here I have taken g of n as n, or you can give any quadratic values and you can substitute and see for which value it is true. Say for example, if I put the value of n as 1, and if I put the value of c as 10, and we'll substitute and see whether this condition is true. So I'll say 2 into 1 plus 3 less than or equal to, constant I have given as, I have taken as 10 into n value is 1. So if you see the value is 5 less than or equal to 10, so this condition is true. So we can see and you can substitute some other value of c and you can find. Say for example, if I take the value of c is equal to 5, okay, and if you consider, so I'll say 2n plus 3 less than or equal to cn. C value I have taken as 5, and let's say n value is 1. So I'll say 2n plus 2n, n value is 1 plus 3 is, we can say 5. So 5 less than or equal to 5. This condition also true. So, but if I make the value of c as 4, if I take the value of c as 4, so if this condition will be true, so here if I again substitute here, I'll get 2n plus 3 less than or equal to c into g of n. This should be the condition. So the c value here I have taken as 4, and the g of n I have taken as n, and the n value will let us consider as 1, and c value it is 4. So 4 into n value is 1, that is, here we'll get, when I substitute this n here, I'll get 2 into 1 plus 3 less than or equal to. So here I'll get 5, and here 4 into 1 is 4. So here this condition is not true. This condition is not true. 5 less than or equal to 4 is the condition is true. So I cannot take the constant value c as 4. So I can take the c value from 5 and I can start the n value from 1. So how can I derive for this function? So I can say 2n plus 3 is our f of n function is less than or equal to c into n for all c value should be 5, and n naught value or n value should be starting from greater than or equal to 1. Okay, so this is how I can conclude for this big O, for we can for any of this problem. So the condition is always this: f of n should be always less than or equal to big O of n, and we have to substitute some value and we have to find it. So we can say our function, whatever value which I get from this algorithm, will be definitely less than g of n, because we are finding the worst case. So it will never go beyond this. So such a way we have to find the worst case. So what is the next notation? Best case. So best case is denoted by omega, right? So how will I say the definition of omega? So I hope you will remember. So anyone, can you remember what is the definition of omega? So here I can say the function, I can say the function. So our function is denoted as f of n. F of n is the function we give for our algorithm. Okay. So I can say the function f of n is equal to omega of g of n, if and only if there exists a positive constant c and n naught such that, so what is the condition here? Always here we are, if omega speaks about the best case. So here I can say always f of n should be greater than or equal to some constant into g of n. So how will be the graph like? So here using omega, we will be, for example, we will be having the g of n here. So that speaks about the best case. So this minimum, it will be taking this. Less than this, it will not go. And when I find our function, it will be like this f of n. And this f of n will be always greater than this. And this place is called as n naught, and the difference between this is called as some constant value, right? So we can, here in this best case, we know our function which we find will be definitely always less than this g of n, and the this function which we get using this omega will be always giving the best case. So it will not be minimum, that very minimum value which we get from this algorithm will be given by g of n. So here also you can substitute some value and you can see is it true. So for example, we'll take the same example. If let us consider our function, or our algorithm is taking a value of 2n plus 3. Okay, so if you substitute here in this, we can see how does it functions. We'll say same thing. So f of n should be greater than c into g of n. So our function is 2n plus 3. Any quadratic equation you can give, as we get here in the PPT. No, so what are the different? This is one quadratic equation, and we have. This is another quadratic equation. So this is our f of n. What is f of n? The quadratic equation or the output which we get from our algorithm. So that is what represented here. So the quadratic equation, consider, let's we get an value of 2n plus 3, and that value should be always greater than or equal to some constant, and let's say g of n can be n. So we have to find for which value it will be always true. Such a way you have to find a value. How can we do? We have to substitute some value for n, and we have to substitute some value for c, and we have, say for example, if I say the n value is 1, and let us consider the c value is also 1. So if I put it here, I'll get 5, right? 2 into 1 plus 3 is 5. It is greater than, both are 1. So if I put here also, so I can say when n value is 1 and c value is also 1, this condition is true. So I can say 2n plus 3, the function is always greater than or equal to c into n for all n equal to or n greater than or equal to 1, or c constant value is 1. So likewise, or if I take some other value, that, so we know from some particular value only this conditions makes true. So that is what we have taken that value here as 1, right? So other than that, here sometimes if you take any other value, this condition may not be true. So such a way we have to find from which value onwards this equation goes true. So likewise we have to find it. So this is about the best case time complexity. And what is the next one is theta. So theta will help you to find the average case. So how does this average case represented? So I can say, as we have said here, we can say our function f of n is equal to theta of g of n for all the values of c and n naught such a way. And how should our f of n condition now? This is now speaking about the average case. So our f of n function should be less than or equal to c2 into g of n, and it should be greater than c1 into g of n. So this is how our condition should be look like, because our graph will be like this. So here we have the function should be an average, right? So consider this is C1 into g of n, the best case function, and let's consider this is our worst case function, C2 into g of n. So our function will be coming somewhere around here as an average case. So here we have to make sure that always our function should be greater than or it should this function should be in average place. So how will I should this f of n should be greater than c1 into g of n, and this f of n should be less than this c2 into g of n. In between this two best case and the worst case it will be coming. So we have to find a value. First, we have to find the value for the lower bound. So, what is the lower bound value? We have to say C1 into G of n less than or equal to f of n. So, for a condition of C1 and n, we have to find the condition true for this, and then we have to find the value for upper bound. So, what is the upper bound? Our f of n function should be less than or equal to C2 into G of n. So now we have to find here also what should be the constant value C2, and we have to find what will be the n value. So such a way you have to substitute and you have to find what will be the constant in this n naught value and what will be this constant C. Yeah, this C2, and here also we have to find what will be the C1 value, and then from that particular value this conditions goes true. So likewise you have to find the average case, right? So I hope you have got it right. I hope you have we have recollected the concept of symptomatic notation. Is it clear? Any doubt? Do you understand, ma?